Hey guys, what's up? Welcome to the next video on stereochemistry. This one we are going to be covering meso compounds. Alright, so what are meso compounds? Well, meso compounds require at least two chiral centers, and they have to have an internal plane of symmetry, okay? So they have to have an internal plane of symmetry, and any R and S stereocenters on one side of the plane of symmetry will be opposite on the other end. Right? So this is obviously easiest to show with some visuals, and so let's just get some examples. So I'm going to draw this compound here. Right? It's a cyclohexane with two chlorines, both wedged, one carbon apart. All right? And so what I'm going to do, let's try to figure out if this is meso. So one of the requirements was at least two chiral centers. Okay? The second requirement was a plane of symmetry. And number three, the R and S stereocenters are opposite. So first let's determine if it has two chiral centers. Starting with this carbon, remember that there is a dashed H there that we don't see. Same for this one. So that carbon in blue has a chlorine, a hydrogen. It has this chain over here going in that direction, and this chain in the opposite direction. Now, because it's on the ring, you may think, oh, it may not be chiral. It's all the same chain on the left and right hand side. It's not. Because if I move one carbon over right here, this has two hydrogens. Whereas if I move one carbon over here, that's a chlorine and a hydrogen. So it's not the same, right? And so that is definitely going to be a chiral carbon. And because it's symmetrical, we can pretty quickly determine that this carbon right over here is also chiral. So we can definitely check off our first requirement. And so does it have a plane of symmetry? All right, well, let's see. I can draw a little mirror almost right there, and we can see that our molecule perfectly mirrors itself, the left and right hand side. So it definitely does have a plane of symmetry. So that gets checked off. Are the R and S stereocenters opposite? All right, so let's see. Let's start numbering our priorities. Let's do that in purple. So our chlorine here would be number 1. The carbon chain over on this end right here would be number 2, that carbon, because it's connected to a chlorine, whereas the one over here that I'm labeling as number 3 is going to be connected to 2 hydrogens. Right? A chlorine is higher priority than 2 hydrogens, so we would assign the carbon with the chlorine as number 2, and this hydrogen right here gets number 4. Now let me just erase these hydrogens over here. Oh. Okay, and so our lowest priority group is dashed, so this is easier. Cross that out and draw the arc from 1 to 2 to 3. You drew this, and it's clockwise, so we're going to have an S configuration. And now let's just erase that to give us some room. And now let's do it again on the opposite side. Chlorine gets number 1, this carbon number 2, this carbon number 3, hydrogen number 4. Cross out the lowest priority group, and it's dashed, so this is our easiest case. Just draw your arc. 1, 2, 3. That looks counterclockwise. Yeah, that looks counterclockwise. So we're going to put S. Right? And I'm pretty sure I just messed up the last stereochemistry here. So let me just redo that really quickly. 1. Oh boy. 2, 3, 4. Yep, that should be R. My mistake, guys. Okay, so we have R and S. So yeah, that satisfies our third requirement that the R and S stereocenters are opposite. And again, my mistake for that. I went a little bit too quickly through that part. And so it completes all three of those rules. And so we can say that yes, this is a meso compound. All right. How about this compound right here? Let me redraw that better. So now I'm going to draw something similar. Now let's look at this. All right. So does it have two chiral centers? Let's check it out. Starting with this one. Well, we remember from the previous example that that is a chiral carbon, right? And so we can just, we know that that is already a chiral center there. And this one over here, it's a dash chlorine, a wedged hydrogen. That's two groups so far. This chain and then this separate chain going in that direction. So yeah, we have four unique substituents on each of our chiral carbons, and we have two of them. So we satisfy rule 1. Is there a plane of symmetry? Let's draw it right there. Well, we can see on the left side we have a wedged chlorine, whereas on the right side it's dashed. So that's not a perfect mirror. It has to be a mirror in all aspects. And so it fails that rule. All right. And if you guys, let's do the RNS configuration. Now, I remember from up there that this is R, so I'm going to skip that one. But let's look at this one. Chlorine number 1. We have a dashed hydrogen here, remember. Number 2, 3, 4. Cross out the 4. And in this case, our lowest priority group is wedged. So whatever arc we make, we're going to say it's the opposite. So we're going to make 1, 2, 3. That looks counterclockwise, which would normally be S, but in this case, because our lowest priority group is wedged, we write it as R. Okay? And so we can see that our RNS stereocenters are not on the opposite ends. So it also fails the last rule. Okay? Now, when you talk about meso compounds, you can more or less figure them out rather quickly just by looking for a mirror. Just by looking for a mirror. But yeah. And so let's move on to what chains will look like, because rings are usually fairly obvious to figure out. Chains are a little bit different. They're not as intuitive. Okay? So I'm going to draw this chain right here. All right? And so let's look to see if it fulfills the requirements to be meso compound. So have at least two chiral centers. So let's start right here. This bromine, the carbon with the bromine. The bromine is one unique substituent. It has a methyl. Remember, there's a dashed hydrogen here, so that's 3 so far. And this carbon chain right here. So those are 4 unique substituents. So that carbon with the bromine is good to be a good to be a chiral carbon. What about this one over here in blue? Well, it's got a methyl, a bromine, the carbon chain, and a wedged hydrogen here. So those are also 4 unique substituents. So it satisfies the rule of 2 chiral centers. And so now we should look for a plane of symmetry. All right. So we would think that we could just go like this. Right. But if you can see, it doesn't really look like a plane of symmetry, right? You have all your proper substituents. The problem is your BRs are kind of on opposite sides. One is wedged, one is dashed. One is pointed up, one is pointed down. All right. So do we have a plane of symmetry? All right. Now, after what I just said, you may say no. But look at it this way. What if I just rotate this bond a bit? So I'm going to take, let's just erase this so I get some room. We're going to rotate that bond, and we're going to get something that looks like this now. Keep this the same. Now, the BR, I did a 180 turn. This was a 180 degree bond rotation, so that a dashed BR going down, remember dash means away from you. So take your pencil, right, point it on a downward angle away from you, and now do a 180 degree turn. You can see that it's going to now be pointed up and directly at you. And so now we can write our BR as up and at us. And now we can draw a little mirror, and you'll see that we actually do have a plane of symmetry. All right. So what they'll do on tests is they'll draw you chains like that to make it harder for you to see that there is actually plane of symmetry and that it is in fact the meso compound. Chances are they will not draw it like that just because that is a little bit more obvious, but be prepared. Now, there's another way to figure this out if you didn't want to do any bond rotations, because I know no one likes bond rotations. What we do is we draw what's called a point of inflection. You look at the center of your molecule, essentially the center of your chain, and you draw a little dot right there in purple. We just erase the red and blue. All right, so we draw a little purple dot. What I want you to do now is look at the left-hand side, and I want you to look at the right-hand side. The left-hand and right-hand side should be the same in terms of all the groups, whether they look like they're the same stereochemistry or not, should have the same things connected to them. That means the adjacent carbons from that dot must have the same things connected to them, as in a Br and a methyl. All right. And if that is true, then we can also check if they have opposite stereochemistry. So what I mean by that is, let's look at the left-hand side of our molecule. We have a wedged Br going up. So on the right-hand side, it should be a down Br dashed. Okay. See, our methyl is planar going downwards, so on the right-hand side, it should be planar going upwards. All right? And so if it is true in all these cases, then we can say it's meso if you didn't want to rotate the bond. Although I do highly recommend you guys get into the habit of rotating bonds, just getting into that mindset, just because when you get to exam 3 material, learning elimination reactions, they love to mess with you guys by rotating the bonds around to make it harder to see what the answer will look like. All right? And so that would in fact also be a meso compound. Now, if you guys want to just go through the RNS configuration, let's go through it the way it looks both ways. I'm going to redraw this here though, just so you guys see that it's the same. Okay? And you could have also just gone straight through and done the RNS configurations instead. That way you can skip the whole idea of point of inflection or rotating the bond, and you would have seen that anyway. So I'm going to start with this carbon in blue. Our bromine would get priority number 1. This would get number 2, 3, and we have a dashed hydrogen, which would be number 4. And because it's dashed, it's our easiest case. We can just cross it out and draw our arc. 1, 2, 3. That's clockwise, so that would be R. Now let's look at our next carbon. Let's do this in red. The Br get a priority. Number 1, this would be number 2, 3, and now we have a wedged hydrogen as number 4. Now in this case, remember, because our lowest priority group is wedged, we now take the opposite of whatever stereochemistry our arc would normally look like. We cross out 4, draw your arc from 1 to 2 to 3. That looks like it's clockwise, which would have been R, but because it's a wedged H, we write S. So you can see that the stereochemistry is opposite, which is good. That's exactly what we thought it would be because we already knew it was meso. Now let's just look over here and prove it to ourselves one more time. Color this one blue. Bromine number 1, 2, 3, dashed H, 4. Cross the 4 out and draw your arc. 1, 2, 3. That looks clockwise, so let's go R. Now let's do this again on the right hand side. This carbon right there, Br gets 1, 2, 3. Remember dashed H over here now, not wedged anymore. We rotated that. That one gets 4. And now we can just cross this out, and it's our easiest way of drawing it in terms of priority. Draw your arc from 1, 2, 3, counterclockwise, and our lowest priority group is dashed, so again, the easiest scenario. So it's exactly what it looks like, which is just S. And so remember, that's exactly what we predicted. 1R, 1S. That should be opposite on the mirror plane. And so this is in fact the meso compound, and I showed it to you guys both ways. One in which the case they'll probably give it to you like this, where they're kind of weird looking, and then one here where we did the bond rotation. Okay, so those are meso compounds. Now I want to also show you guys one thing. They could ask you on a test how many stereoisomers does a specific compound have. You must be careful when talking about meso compounds. Okay, for example, these two compounds, right? They may look different. We can tell that they're meso because they have 2 chiral carbons each, and they have this internal plane symmetry, right? Now, they are the same compound, right? Look at the compound on the left. It had wedged chlorines. Both of them are coming, remember, because wedge means that it's coming at you, so those chlorines are pointing at you. If I take that molecule, imagine my hand grabs this little side right over here. I grab it, and now I'm going to flip it so that we now have it like this almost. So my hand grabbed it on the left-hand side. Now I flipped it so my hand ends up on the right. That's a 180 degree flip. Okay, 180 degrees. That means that the groups that were coming at you, because we just flipped it 180 degrees, are now pointing away from you. So I can take the wedge chlorine molecule, flip it 180 degrees, and superimpose it right onto that compound, indicating it is the exact same thing. Alright? So be extremely careful with that. Alright? So be very careful with regards to meso compounds and talking about stereoisomers in terms of how many we can get. Because those are not 2 separate stereoisomers, they're the same compound. Okay? So I hope this video helped you guys. If something here didn't make sense, please feel free to email me, talk to a TA. If you see me maybe in the chemistry building, please don't hesitate to stop me. And if you have a question, I'd be happy to help you guys out. And I will see you guys all in the next video.